Hello and welcome. This paper is entitled Historic Plant Biology Experiments Integrated with Modern Technology. Okay, so we're looking at basically senior level high school biology, some traditional experiments that would have been done in the past, some still do it, and trying to integrate these with modern technology and some of the insights that has given us. So the aims and objectives of this work, the overall aim is to revisit historical botanical experiments in the light of modern IT revolution in education. And the objectives, one, is to reenact auxanometer and potometer experimentation with sensors. That's the, if you like, the pragmatic part. And two, to address plant blindness. Okay, the cognitive bias that people have against plants, to improve the integration of IT into biology, practical work, and science in general. So there's barriers to teaching, and very often there are barriers to learning, and that's what prevents children learning. But one barrier to learning is, of course, are the barriers to teaching, that things that stop teachers teaching what they should be doing, I suppose. And I mentioned a cognitive bias called plant blindness. Okay, and this would be basically, as it implies when you come to teach, a general avoidance or reluctance to deal with plant biology, despite the fact that the plants are models for animal or human biology. So even though we're certainly in Ireland and in the UK, you're supposed to teach about plant biology, there's a general reluctance to do that. They're considered, for the children, the boring parts; for the teachers, the parts they're less certain with, unless they have a degree in botany, which is increasingly unlikely. You find that these are parts of the curriculum that are skimmed over. When we look at, for example, some student teachers who are going to be biology teachers in high school, and we are asking them, okay, I want you to tell me, please tell me, what are the topics that you don't like doing at all, okay? And the least interesting and the least likely to teach, plant biology comes way out on top as the single most set part of the curriculum. Now, of course, this is a problem because in Ireland, biology leaving certificate examination, it's half animal biology and half plant biology. So you're already got a problem here. But it's not considered a problem because of the ability of students to rote learn, to memorize information rather than understand the information that they're doing, and so therefore still getting the grades that they need to go to university. Interestingly as well, and needs to be dealt with elsewhere, ecology comes up as the second single most negatively impacted topic, ecology. And that very often can be simply because there isn't field work done as would have been in the past, okay, and less of an emphasis on field work. But plant biology, there's definitely a problem there. Okay, so very often you have schools and they contain lots and lots of different equipment. Sometimes they're hidden away, they've been disassembled, they're not in use, and sometimes they're simply dumped because nobody has remembered how to use them. That information is not passed on. And also the universities, because they don't teach this classic botany to people anymore. They teach applications rather than what we call fundamental botany and biology, organismal biology. They're teaching more biomedical, biochemical, biotechnological biology. And so the use of such devices as these are really just what are left in, and it's older schools that would have these. Older schools that are obviously would have been well equipped. So you've got two examples here. They're both devices for helping to measure the growth of plants. And the top one is the one relevant for this paper because one of the things I had to do was make a simpler version of it, rather than use the artifact from our science museum and our herbarium. And instead of the pivot point on the axis just being a nail, we put a sensor there, as you will see. Okay, so you can see that it's basically one large finger pointer. At the short end of the beam, a thread runs and is attached to a plant, and it obviously has to be a plant that can tolerate that kind of attachment. And the arc is then where you have a series of measurements. It's basically, it can be an angle, or it can be transposed so that it actually reads centimeters or inches if it's in old money. And you can read that, say, daily to see where the pointer is going to. Okay. Now the problem, of course, with this arc auxanometer is that if the plant wilts at all, if there's a fluctuation in water content in the plant and it wilts slightly, you get as if the growth is not as significant as you would have otherwise found. In the Pfeffer auxanometer, Pfeffer gained from the 19th century. He's a extremely important German botanist. He had a huge influence on the teaching of botany in schools, in not just the German-speaking world but the English-speaking world. And he developed a device where it does the same thing as we've before, but there's a clockwork mechanism in this case. You can see it here in the middle of the photograph, if that's visible, and there's a small rotating drum which you attach some paper to, and a pointer where you can put a pen made out of, say, tin, and put ink in a little well in that, so that it will draw an ink line as the plant grows. Okay. But the thing is that you can see, I don't know, can you see from studying these pictures how, for example, you can actually convert them or change them into things that can be integrated with IT. What the point of this paper is to see, yeah, well, yes, you can do that. So measuring water uptake in a plant using a potometer, okay, is a very typical sort of situation that comes up in textbooks, examination papers, you know, but it's very old. It comes from the 19th century. All right, it's many teachers avoid doing the actual experiment though, because it's a little bit finicky, as we say in English, a little bit tricky to set up to get it working. And what it basically does is that the plant, water evaporates from the leaves. As water moves through the tube, you get a drop in the level in the pipette, and you take the reading manually. Okay, so what I did is that instead of having an open pipette, we have the closed tube, and at the end of the closed tube is a BMP 180 barometric sensor, and that was interfaced with an Arduino Uno connected to the computer. And the pressure, and it's a pressure, well, decrease or increase, would you say? Of course it's a decrease. Okay, so as the water evaporates from the leaves and it's drawn up into the plant, the water is drawn away from the tube here, and there's a negative pressure in the air-filled specimen tube. Okay, so there's a question, of course, whether a threshold negative pressure is reached whereby the rate of the water uptake is affected. As we would know from various experiments, that you're a long way off, so that's the sensitivity isn't actually impinged on there. And of course the typical thing is doing experiments on varying the environmental conditions surrounding the plant, and then comparing those. So as the water in the silicon tube is taken up into the plant, the atmospheric pressure in the specimen tube reduces. It's registered by the sensor and then logged on screen. Okay, and you can ignore a lot of the temperature readings because I hadn't calibrated that, and the pascals are not correct in terms of the units, but those are our preliminary results, which shows a fluctuation when the pressure is changed. Now back to the arc auxanometer. Again, it's a typical historical experiment to growth in plants, developed in the 19th century. It's frequently find textbooks again and curricula around the world, but teachers generally wouldn't do this actual experiment. They would just simply talk about it. Okay, I think that's a pity, because it is actually a simple one, and it could be, you don't need the specialist equipment. It could be made from scratch, just with simple items that would be typically found in the lab. So here we have an auxanometer. It's a simple arc auxanometer. And what I've done here is I've just made one out of scrap pieces of wood. The sensor I've chosen this time is not it basically, I'm reusing some old sensors from a Lego Mindstorms kit, but the first one that came out, which of course you can't really use easily anymore, otherwise I would have kept this completely in Lego. But the brick, it's very hard to get those to interface with computers now, because they were typically beamed with infrared, and it's a trick to get a computer that'll run the software for you. And even if you get to that stage, it's very difficult. So I could have, you can buy, of course, a rotational sensor from Vernier and other companies. They tend to be a bit on the pricey side, but here I had one for nothing. So and the pieces of wood didn't cost me anything. So I'm really making use of recycled materials which I like to think is in the style of teachers from the past. So basically, I hacked the sensor so that it can plug into the Arduino. It's only a simple 2-lead situation. As the plant grows, of course, the straight beam rotates, and that's detected by the sensor and logged by the Arduino. And therefore, you can do various experiments and so on. You could, for example, have, which in the past wouldn't have been done, but you could have, for example, a series of these set up, and identical plants and all of the different varying environmental conditions, such as nutrients, water, light, and temperature, all seeing does that improve growth. Okay, so that can be all done. Again, with the beam is rotating, you do get a variation in the thing, and that's logged, and that's shows it's actually working. But of course, ultimately, well, did that work with the students? Did it change their attitude? Okay, and that's actually, firstly, it's difficult to do, to change the attitude of people, and secondly, it's difficult to see are there any changes taking place. So following the lecture workshops, the students were then probed for a change to their attitude to plant biology. They were asked to score a differential based on 5 variables. For example, how they thought of plant biology before working on the digital interfacing of historical plant experiments using the 6-point Likert scale. And the 5 variables were overall satisfaction with the work done in this area, integration of technology with biology, homemade resources, using homemade resources, programming the Arduino, and then history of biology. Okay, the scores did show a positive differential. So there was, from looking at what we might consider an ideal subject or an ideal sort of set of results, we did see a certain movement towards that ideal, but it did not prove to be statistically significant. In order to generate a statistically significant change, a larger or broader study is necessary. Okay. What we did see when we did a scatter of the students, as they're shown, each variable in the graph here is a student, and we've used all 5 of those variables to denote their position on this space. And we can see, for example, that there's a broad consensus with a large number, but there are certain students who do not fit with the consensus. So number 22, which is seen in the bottom right hand quadrant, is definitely an outlier. What we do is that we look at number 22 and we see where they're different. Okay, and what happened with number 22 when you look back on their 5 variables and where they looked at it is that there was something that stood out, and in his case, he absolutely was not happy with the work that was done in this area. Okay, so he was unhappy. So that's how he was different from the others, and that was enough to put him down there. Okay. In other ones, what happens is that we see the other ones who are variable 27, 29, 25, and 23. They were different in that they were had a very positive, if you like, perspective on the integration of technology with biology, more than say the others. But again, mediocre in the overall satisfaction. So slightly contradictory. Okay. However, the overall scores did show a positive differential. So it gives me something to work on for future work. Science is human activity in its modern form has a history, development spanning 400 years at least, and biology is no exception. Not only is science per se a historical entity, but so too is school science, according to Leahy. And the introduction of modern information-based technologies may seem incompatible with previously well-known experiments, simulations, computer models, replacing physical hands-on experimentation. For example, see Winsberg 2019, and this would be in line with the so-called Moore's law, which suggests that as computers become more widespread, they replace typical human-based activities. However, rather than replace, modern technology can enhance, as demonstrated by the two examples described here, and not merely for its own sake or a call out to the past, but as a means to tackle cognitive biases such as plant blindness. Okay. Just on that point, when the students were challenged as to the fact that their disapproval of studying plant biology was based on a cognitive bias, it did actually help them become more kind of attenuated to the possibility that maybe they should look at it, given that they were going to be professional teachers. The students do take some convincing, and by the time they arrive in the university, cognitive biases are already deeply ingrained, and they do require a great deal of work to dislodge or to work with. So this work will continue into the future with that vein in mind. So thank you very much. I hope you find the paper interesting.